Another example of a second-level application is AITION. AITION is a knowledge discovery tool developed by the Computer Science Department of the University of Athens. AITION in Greek means cause or explanation, which is the origin of the word etiology. The main objective of AITION is to provide clinicians with novel means of discovering, evaluating, and exploiting new medical knowledge and assisting them in the prediction of diseases and extraction of patient trends. It is built around a graph-based causal and probabilistic framework that uses so-called Bayesian networks and the Bayesian framework to identify direct and indirect complex correlations. AITION is built on Healthy Child's data sampler, and the University of West England's Healthy Child data sampler bridges the gap between clinicians and Healthy Child's knowledge discovery applications. The Healthy Child data sampler assists the user by generating a sample data set from the Healthy Child data repository. Once the search criteria is specified, the Healthy Child data sampler extracts patients' records from the Healthy Child data repository and generates a data sample. This sample data can then be fed into Healthy Child knowledge discovery applications like AITION for further processing. Once the data has been extracted by the data sample into AITION, users are able to see all the correlations for a specific disease on one graph and interact with them to provide inferences and reasoning. Harry Dimitropoulos will highlight for us some of AITION's functionalities.
Here we can see the inputs to the AITION system. We can have a number of observations, clinical features, variables or features from, say, imaging, things from the Healthy Child database, basically. We can add a priori knowledge from the clinicians, and we can also link to ontologies. These things go into AITION where we can do a lot of things, but some of the things will be to find significant features, and the main interest is actually to represent the relationship between these variables in a graph-based probabilistic network. We can then use that information to feed back to ontologies.
In this example, we can see how AITION can be applied to juvenile idiopathic arthritis to discover dependencies between different variables, with the aim of deriving knowledge about prognostic factors, treatment response, and outcome predictors. So here you can see a subset of the problem. 17 variables have been selected that come from different areas: demographics, clinical data, assessment, laboratory, and medication. From these data, AITION is able to find the most important dependencies and independencies and produce a graph which summarizes the data set whilst also providing the causal probabilities. One point that should be stressed is that this is one of the ways in which Healthy Child has achieved one of its key goals. Such a goal was to vertically integrate clinical data from the 4 clinical centers, in the sense that each of the variables comes from a different source. Let's now listen to Harry Dimitropoulos again about how a priori knowledge can be added by clinicians to AITION. Adding a priori knowledge to AITION is a key to utilizing AITION in a clinical environment, as AITION would otherwise consider all the data to be of the same order. This can be done in 2 ways, as Harry Dimitropoulos will explain.
I mentioned in the second slide that we can add a priori knowledge from the clinician. That can be done in 2 ways. One way is the clinician can directly interact with a graph, and for example, on clicking on some variable, they can add new links or remove links or swap things around. So if they think that from their experience some things shouldn't be as they are, they can change the graph, and then the probabilities will be recalculated and see if produce better results. Another way of interacting with that is to set layers before building the model, which is for order the layers in a way to represent the causal characteristics. For example, in the first layer we can have things like demographics, and at the bottom treatments, so that because AITION Bayesian networks basically look only on the raw data without knowing what comes first or second. They try to find that out just from looking at the data. It makes sense to add any knowledge that we have. For example, we don't want taking drugs on steroids to show that your age is under 3. It's the other way around.